Good evening, everyone. I am Banduka, the coordinator for technical events in Civil Engineering Sectional Committee. So this is the lecture series on structural designs of bridges. So I would like to invite our Civil Engineering Sectional Committee Chairman, Engineer Mrs. Kamala Gunawardana, to do the welcome address and continue. Over to you, Madam.
Yeah, thank you, Engineer Banduka. Actually, it's a great honor for me to do this today's welcome address. And first and foremost, I welcome all the participants who are joining online today. And our resource person today is a well-known academia Professor Tisan Jaisingh, and welcome you, Professor.
Thank you.
With your acceptance to conduct this series of lectures from today onwards.
Yeah.
As you are aware, at the Civil Engineering Sectional Committee conducted about 46 webinars on technical and non-technical, out of which almost half of those were lectures from Jaisingh conducted on different subject topics and designs in high-rise buildings, especially on Europod applications, during his chairmanship of the Civil Engineering Sectional Committee in previous session. Today, we are starting the new lecture series under the title, as Babula said, Structural Design of Highway Bridges, and today's session 1 on the subtitle, The Reuse of Reinforced Concrete for Highway Bridges. I want to emphasize that we do carry all these lectures and events exclusively for the benefit of our members, and actually many events planned by the Civil Engineering Sectional Committee. Some are done and some are on the way, and please be with us, join these events as far as possible, and that itself actually an appreciation for our work from you all. Though the resource person today is well known, but as a formality, let me introduce him. So I will read out few of his achievements, some important titles he is enriched with. Professor M.T.R. Jaisingh gained his first degree in civil engineering from the University of Morocco in 1987, while winning several special awards that include in the gold medal for the best engineering graduate and also Dr. N.S. Kulasing Award for the best civil engineering graduate. His experience with highway bridges is from far back from 1984 as an undergraduate in at that time, with precast post-tension beams of 23-meter beam. His PhD is one on the use of artificial intelligence for the structural design of spine beam highway bridges. That was in during 1988 to 1991 at the Engineering Department of University of Cambridge. Since returning to Sri Lanka in 1992, he has been active in pursuing research and developments associated with highway bridges and flyovers. He has designed one of the widest and longest flyovers in Sri Lanka, Orgodatha flyover, which is 560 meters long and 70.6 meters wide, in addition to few other long span highway bridges as value engineering solutions, which is very important. He has also developed a few methods to have very cost-effective bridges with reinforced concrete as well. He wishes to share his vast knowledge with our engineers through this lecture series from today onwards as part of our Civil Engineering Sectional Committee activities. Please enjoy this important lecture series and abstract the essence of it. Before handing over the floor, I request Banduka, who is the coordinator of technical events of CESC, to proceed the balance proceedings today. Without further ado, I invite Professor Tisan Jaisingh to take over. Thank you.
Thank you, Engineer Kamala, for that introduction. Can you see the screen?
Yes.
Can you see the screen?
Yeah, can.
Yes, sir. Yes, sir.
Okay, thank you. Right. So today we'll start this lecture series, and today's topic is the use of reinforced concrete. But before, what I thought was, it would be good if I can give you some overview about bridges. So there may be some engineers who are more familiar with buildings, who would like to have some kind of overview before we start going deeper into the subject. So the lecture series is structural design of highway bridges. And so the overview of the presentation is I'll first do some introduction, and then I will tell you about few important parameters applicable for bridges. Because if somebody asks a question at the site, it's sometimes we say, okay, I have to check on the BS code or Euro code and get back to you. But a better approach is for you to have a small database on bridges, where all the important parameters are stored in your mind, in your brain. And when a general question is asked, you can give a reasonable answer. May not be 100% accurate, but reasonable answer. So there are so many numbers we can remember when it comes to bridges. So I'm going to highlight some of those numbers. And then the simplest possible bridge is just have a slab supported on two abutments, and that's a bridge. And this is the oldest form, because earlier people used logs, the timber, trunks, and created a bridge which looks like a slab. So when you place so many timber trunks close to each other, and then place soil on it, you can make a bridge. So that's a type of early bridges. But these days we like to use modern materials for bridges, so we can have alternatives for slab bridges, and then how they have evolved. And then we can also look at value engineering solution for flyovers, how we can use value engineering. That's again a very important topic, especially in today's context, because we are having a financial crisis. In a financial crisis, it's very good if we can come up with very economical solutions rather than typical solutions. So that's where value engineering becomes very important. And then another topic that you can see very much applicable to today, where we have so many elevated highways and expressways. For example, on the outer circular road in the Malabeg area, you can see the road is elevated. The reason is it's a floodplain. So it elevated bridges or expressways, if we need continuity to avoid expansion joints for about 5 to 6 spans. Only, we'll have only one expansion joint. So continuity for the other spans, the bridge is continuous. So continuity is a very important topic in today's context. And then, how we deal with abutments and foundations. And also one of the key problems that we encountered in many of the southern highway bridges up to Martha was called DEF, delayed ecingite formation. So we can talk about that problem also, just to get some overall idea. And later, I can actually tell you a lot more information about it and how to avoid DEF. And if the time permits, we can come back to that topic today itself. And the piers and foundations. And the last topic is pre-stressed concrete continuous bridges. And you might ask, why is it applicable for Sri Lanka? And it is actually applicable because today we are having a 5.2 meter long elevated highway called Port Access Road being constructed by a Chinese contractor, where the bridge consists of two box girders or spine beams, where it is made continuous. It's made continuous. It's constructed as a truly continuous structure. Whereas, if you look at most of the other elevated highways in our expressways, they are actually continuous structures only for live loads. They are not the real continuous structures. They are precast pre-stressed concrete elements made continuous by using pre-stressed or reinforced concrete. So there are so many different types of bridges that are available in Sri Lanka. So it's very important for us to first identify what are the different types of structures that we come across in bridges. So to start with, I will stop sharing and just to tell you a little bit about historical evolution of bridges. So I'll stop share. And can you see the whiteboard now? White sheet? I hope you can see the white sheet.
Yeah, can see.
Yeah, okay. So if you look at the early bridges, it could be a tree trunk on two supports. And then people found wrought iron. Then they went for bridges like this. Bridges like that. And we had one end fixed, other end on rocker and roller bearings. We put it on a bearing. Then you have to ask why. Why bearings? Now steel is a very good material for tension and compression. But in compression, these thin sections would have a problem. What is the problem? They buckle. They buckle. When you compress a thin steel section, the section can buckle. So the section can buckle like that and fail. So if you have a bridge like this and it is fixed, what could happen? What would happen? There will be temperature induced stresses. So because of that reason, we actually, people thought, okay, if you have a bridge, it has to be on roller supports. And you can also have rocker supports also. That means it can rotate and move. So today we call them bearings. We call them bearings. Let's check that. One. Today is 14th. Right. Right. Now we see what happened. So the early bridges were needed for steam engines. For steam engines, and those bridges were out of timber. But because these steam engines have charcoal and coal, so sometimes these bridges can be damaged by the dropping. So when these burning ashes drop on the bridge, they can suffer damage. Then people thought, okay, let's use wrought iron. So let's use wrought iron, and then they constructed bridges like that. And in 1930s onwards, people thought, okay, let's have concrete for bridges. And you put it on a rubber pad And rubber pad can allow rotation and expansion. This rotation would be very small. And then they thought, okay, let's go for beam bridges, thin slabs, which are converted to bridges by placing the beams like this, precast beams. And then you put concrete. So you get a slab, a pseudo slab. So it looks like a slab. And when they did this, they did it first in the coal countries. Okay. They thought, okay, concrete bridges also need bearings. They also need bearings. So you get expansion joint, premix layer, and then when you pass this joint, you can hear a sound from the tires of the vehicle. So if you look at a country like Sri Lanka, if you look at our morning temperature, 23 degrees, even afternoon temperature, 32 centigrade, our temperature variations are very small. So even if you don't have expansion joints in Sri Lanka, what will happen? This will expand during the daytime. And then it can induce a compression on these members. And because we are having fairly thick members, the chances are they can take this compression very easily and they will not buckle. But instead, it can lead to some pre-stressed concrete situation in the beams. So basically, we have been doing some studies for Sri Lanka. And what we found was expansion joints are not really necessary for bridges constructed in Sri Lanka. So that's why you can see that we can easily have six spans or even 10 spans as continuous, and then we can have one expansion joint. Because at every expansion joint, you can hear a slight sound from the tires. So that can be minimized by making the bridges continuous. And our usual practice has been having about 6 numbers of 30-meter span. So every 200 meters, you would have an expansion joint. But our current work shows that, even if you have one joint every 300 meters, the chances are that nothing can go wrong in our bridges because our temperature variations are very small in the tropical lowlands. But in the upcountry, sometimes, you can consider having having lesser number. But in upcountry, we can't have very long bridges. The reason is, the topography does not allow us to have continuous roads. So the chances are that, most of our bridges and flyovers and expressways where continuity is needed, those will be in the tropical lowlands with very low diurnal temperature variations. So daily variations are very small. Because of that reason, even though the bridge will become heated up during the daytime, still it's possible for us to have a bridge where the expansion joints are only once in 200 to 300 meters. So that's one important point that we have to keep in mind. Now I will go back to the presentation again, and I'll stop. I'll share the screen. Right. So if you look at the introduction, so what is the difference between a bridge and a roadway? Generally, the elevated highways or bridges are much more expensive than the embankments or the normal roads. So if you construct the road on the ground, or if you construct a small embankment and construct the road, the cost can be much lower. Whereas if you decide to go for an elevated highway, the cost can be much higher. But again, you have to look at the safety aspect. If it is a real floodplain, then you'll find an elevated highway is a much more preferred mode than an embankment. So if you look at Katunayaka Expressway, it's on an embankment. Whereas if you look at the outer circular highway, it's lot of places it's elevated. And in the same way, if you look at the road beyond Matara up to Mattala, the Matara area is the Nidula River floodplain. So in those areas, again, the road is constructed as an elevated highway. So the cost of an elevated highway can be much higher. But if you ask for a normal figure, I would say today's cost, it should still be around. If you go for a very economical, optimized design, the cost can vary between 6 to 10 billion rupees per kilometer, 6 to 10 billion rupees per kilometer. But if the road is wide, having like 6 lanes, then the cost can be even higher. But the cost has to be at least 6 to 10 billion rupees. Whereas if you are going to do it on an embankment, it can be something like 3 to 6 billion rupees or slightly more if you are going to encounter very weak soil conditions where a lot of soil improvement has to be done. Then it can be even, it can go up slightly. So those are just numbers. So just for information. And the simplest possible bridge is a slab bridge up to 20 meters. And generally, if the span is more than 14 meters, it can be post-tensioned. So I can tell you something that happened in France. So they had to develop their road network in a big way in 1960s onwards, because a lot of the road traffic increased a lot with the economic development in those countries. And the vehicle, you know, a vehicle per family is a concept of the USA. It's a USA concept. But Europe, the concept was very much different. It was a concept of public transport. It's a concept of public transport. However, in 1960s onwards, you know, this they saw some difference in the policy, and then they had to develop many rural roads. So they found that, you know, up to 20 meters, the easiest thing is prepare some homework and pour sand. Before pouring, you will just have some pre-stress tendon, and after pouring, you will stress it, and it will make it a PT post-tension bridge. And sometimes they even had 2 spans done in one go, and so you would have pre-stressing tendons like this. Then you will ask, who constructed these? Those were constructed by farmers off season. So during the winter season, they can't do cultivation. So they might do bridges in the season that they don't have farm work. So you can see, that's why, slab bridges became so popular, because, people without much technical training can construct these bridges once there's sufficient supervision, because these bridges are very simple. And then what happened was, Europe was having a lot of highways, A-class roads. And then in 1960s, again, they started constructing what we call motorways. In those countries, in the Europe, England, they call it motorways. And in Germany, autobahns. So they use these ways, and expressway is, I think, maybe a USA word. And in Sri Lanka, we call it expressway, which is access control. And so they had A-class roads, and the highway will come like this with abutments. So these highways had to be completed very fast. So what they found was, there's no way that you can have formwork here because it will block the road. So the ideal solution is to go for something precast and place concrete. So the disturbance to the traffic here is minimal. The traffic here is minimal. So that's how this precast construction evolved. And later they found that this precast construction is not very economical. So because the dead weight is too much, and then they went for this type of construction. And later they thought, now this will not allow them to inspect, so let's not have all these beams touching each other, let's keep a gap. And that led to Y beams. And these M beams. These inverted T. So that's how the bridges evolved. So it's not one process. And then you'll ask, what are other parameters that helped? In 1964, one person called Soko developed a stiffness method. Under that, he derived something called grillage. So what is the difference between a frame and a grillage? On the frame, we apply the loads on its own plane. On the grillage, we apply the loads perpendicular to the grillage. So on the frame, we get axial forces, bending moments. Whenever you have bending moment, you have to have a shear force. And here you get bending moments, shear forces, and torsional moments. No axial forces because it's loaded in the plane perpendicular. So you'll get bending moments, shear forces, and torsional moments. And this grillage modeling using computers made the life of the bridge engineers extremely simple, because earlier the problem is that you have a plate, you have different vehicles using it, finding the bending moment torsional moment, shear force was a huge task. So bridge engineers spent hours and hours and hours and days trying to find the maximum bending moment induced on a bridge. They spent a lot of time. But with the computers and also once the grillage was developed, things became very much better for them because they could get fine bending moments, shear forces, torsional moments in a much shorter time. So this made huge difference to bridge engineering, and many started thinking, okay, bridge engineering could be a career because the life became much easier with the introduction of computer-based analysis. So that's another advancement that made bridge engineering a popular area of specialization. Right. So if you look at to avoid formwork, straps have been modified with precast beams and cover up to 18 meters. So still a penalty has to be paid due to the self-weight. So hence there was some room for improvement. For long spans, precast and inset cast methods can be used. And as I told you, now people generally use 30 to 35 meter long precast beams. Generally eye girders if they are pretty long. Otherwise, the standard Y beams and M beams can be used. But then we are actually using even continuous pre-stressed concrete bridges in Sri Lanka. And one is the currently one that is currently being constructed. About 60% of the work is already over. 5.2 kilometer long port access road, and then we have Banampitia bridge, and also Japanese friendship bridges, 2 bridges close to Demo 800. There are 2 bridges, and those 2 bridges are also continuous pre-stressed concrete bridges. So we have few continuous pre-stressed concrete bridges in Sri Lanka. So let's look at the loads on bridges. So bridges are supposed to carry moving loads. But when you are designing, we design the bridge for static loads. So there are different types of loading. If you look at the British standard, we have type A loading consisting of a UDL and an IFH load. And you will ask how this UDL is developed, and this is how it was done. And so basically it is a series of trucks weighing 24 tons, and the length is about 6 meters. And you have another truck, another one, and then when you look at the effect of this, so you have a lane which can vary from about 2.3 meters up to 4.8 meters. So generally, this is a variable parameter. So a lane which is about 3.5 meters, and they found that this load can be about 30 kilonewtons per meter per lane, giving an intensity of about 8.5 kilonewtons per meter squared. So if somebody asks of what is the kind of load that you generally use in bridge to design a bridge, what is a reasonable value for to get some idea about the kind of loading on a bridge? What is the answer? It is about 10 to 8.5 to 10 kilonewtons per meter. So that's the kind of answers that you should have. If somebody asks what is the load in a building, if it is going to be an office building, what is the answer? 2.5 kilonewtons per meter squared. If it is going to be an auditorium with fixed seating, it's 4 kilonewtons per meter squared. If it is going to be a hall where you can expect a large crowd to gather, the load is about 5 kilonewtons per meter squared. So that's why you will find in pedestrian bridges, we generally use a value like 5 kilonewtons per meter squared. But if it is a bridge where the vehicle traffic can be expected, then a good value is about 10 kilonewtons per meter squared. But generally, it can be slightly lower than 10. But you can just keep in mind, when you have crowd loading, when you have an office, it's 2.5. So if we start with the house, if you have a house, it's 1.5 for bedrooms, 2 for areas people can gather. So living area has to be 2. If it is an office building, 2.5. If it is an auditorium with fixed seating, 4. If you expect crowd loading, 5. Even in a bridge, pedestrian load is about 5. And then if it is a vehicle, the load is double the pedestrian load. So it's 10, or it can be slightly lower than 10. So when you know these numbers, it's very good, because when a layman asks a question, when general public asks questions, you can always immediately give a reasonable answer, so that they will feel that, the engineer to whom they are speaking is very knowledgeable, because they can, whatever the question asked, they can give some reasonable answer. So as engineers, it's good if we can develop this kind of databases. On whatever the subject area, it's good to have some kind of database. Now I'll share the screen again. So then, in addition to that, now we are talking about the effect of axle. The effect of axle is taken into account by using a load which is having a total magnitude of 12 tons or 120 kilonewtons, 12 tons. And we place it very close to the abutment or the support if you want to get the maximum shear effect. We place this in the middle of the span when you want to get the maximum effect. So if you look at 120 kilonewtons and the lane width of 3.5, 120 divided by 3.5 is about 34 kilonewtons. So when you are analyzing a bridge, we can say we are going to get a UDL. And if you are interested in the maximum shear, then this 34 kilonewton load close to the support. I'm considering a meter width of the bridge, meter width. On the other hand, we like the maximum effect for bending moment. We place this load in the center. Now you can see why the load evaluation has become difficult for bridge engineers. If it is a building, we just give an average value and we design for that average value, like 4 kilonewton per meter squared or 5 kilonewton per meter squared. But in bridges, the vehicles are moving. So we have to consider the fact that these moving loads can actually give different values for the maximum depending on how we are going to place it. So that's why the bridge engineers have decided that they are going to make use of influence lines. So that's why the influence lines were all developed, because people found now you are not going to consider the static loads, we are going to consider the moving loads. So one of the simple example is if you want to get the maximum effect on shear, place the concentrated load or knife edge load pretty close to the support. Whereas if you want to get the maximum effect, place the knife edge load at the center of the bridge. And then if you want to get the maximum effect in a continuous bridge, what are we going to do? We are going to load both spans simultaneously so that you can get the maximum effect over the support. On the other hand, if you want to get the maximum moment in the span, we load only one span in a two-span continuous bridge. So you can see for one bridge, you can get so many different combinations of loading. But not only that, when we can actually place the vehicle, this is the bridge, parapets. We can place the vehicle here, or it can come to the middle, or it can come to one side, or both lanes could be loaded. So there are so many different options when it comes to bridges. So that's why, you know, bridge engineering is very different to the highway, the building designs. The reason is there are so many different combinations that we have to consider, and because we are having so many different combinations, we have to spend a little more time finding the maximum moments that can possibly act on a bridge. So now let's see. I'll share the screen again. So then in addition to that, we might have very abnormal vehicles transporting very heavy loads like generators. And if you look at the Kukleganga project, when the Kukleganga project was under construction, they had to carry very heavy generators to Kukleganga area, the power plant. So they found that, you know, most of the bridges are not capable of supporting the kind of load. So they had to strengthen the bridges temporarily to allow these loads to pass. So, but we cannot be doing that type of things all the time. So when you are designing a bridge, you have to design it for very abnormal loading. So abnormal loading is comes with 1 ton per axle, and the number of units can be 25, 30, or 45, or 45. So it's a vehicle like this, 4 wheels. The contact area of the wheel is that it will exert a pressure of 1.1 newtons per millimeter square. So then we have another 2 axles, and the distance between 2 axles is 1.8 meters, and the clear distance between these 2 axles is 6 meters, but it can vary to 11 meters, 16 meters, 21 meters, and 26 meters. So you can have 4 different values. And you will ask why? Why do we need vehicle of different length? In a continuous bridge like this, sometimes you'll find the bridge span is so much that we can place the whole 6 meter, 6 plus 3.6, 9.6 meter long vehicle fully within one span. The span is large, and the width of the vehicle is 3 meters, but the overall width of the vehicle is 3.5 meters. So you might find this possible. On the other hand, you might find this is a different possibility. Now, in this case, you get the maximum moment at here, bending moment maximum. Here, you get the bending moment, maximum value of bending moment at the support. So, you can see different scenarios are possible. And because of that, we are asked to vary the length of the, vehicle. So, I'll share again. And the magnitude is 1 ton per axle. So if you have 25 units, 4 axles, 100 tons. And just imagine a vehicle of 10 meters of length, about 10 meters of length, having a weight of 100 tons. And if you look at the heaviest vehicle on our roads, one of the heaviest is this Ashok Leyland or Tata 10-wheelers with flatbed. And on a flatbed, we can have 600 bags of cement. One bag, so 20 bags of cement is 1 ton. So basically, 600 bags of cement means 30 tons. 30 tons for the truck, the load. And the truck is also heavy because it's consisting of a heavy engine, because it's a powerful vehicle, axles, all that. So the weight of the vehicle also can be about 6-7 tons. So if we assume that the weight of the vehicle to be about 10 tons, close to 10 tons, so we are talking about 36 to 40 ton vehicle over 10 meter length. Then if you look at the kind of the lowest abnormal load, HB type of load is 25 units for minor roads, and for any major road the minimum is 30 tons, 30 units of HB, 120 ton vehicle. But if you look at one of the few bridges, especially even this port access road, has been designed for 45 units of HP or 180 ton vehicle. And we designed this, we developed a value engineering solution for Orugodawatha flyover, again, area where a lot of trucks, container trucks are operated. So because of that reason, knowing that it's an area where a lot of container trucks can be operated, we actually designed that for 45 units of HP or 180 ton vehicle. So if you have designed for 100, 120 or 180 ton vehicle, if our actual vehicles are in the range of 40 tons, you can see there's a huge inherent reserve capacity in bridges. So if you design a bridge with a great deal of care, you will find that those bridges are actually very safe, very safe. So if you are a bridge engineer, if you have performed the load evaluation properly and got a reasonable system to resist bending moments and shear forces, then chances of anything going wrong is pretty remote. Why? The reason is we have already analyzed the bridge for a very heavy vehicle like 100, 120 or 180 tons, but the likely maximum loads may be around 40 tons. Because when you compare the weight of a car, which is about 1.5 to 2 tons, even a double cab is about 2.5 tons. If you have a 10-wheeler carrying 600 bags of cement, followed by 2 double cabs, you can see the weight of double cabs is not very significant. When you consider, so can generally consider the weight on the beam can be about 40 tons, but the same beam arrangement has already been checked for 100 tons or 120 tons or 180 tons. But on top of that, we have actually used some partial factors of safety. So overall, when you look at the overall picture, you can see the highway bridges that we design to either British standards or Euro standards. they are going to be extremely safe structures. And there will be a huge margin to allow for variations, because we do not have any control over the type of vehicles that people might use on the roads. And you would have seen, if you have been to Mayangane area, there's a road that connects the Rajamawata with Mahiyangana. And Mahiyangana area is well known for its sand deposits. So you will find that they used to actually weigh the lorry, because lorry drivers used to overload the lorries. So they used to even weigh the lorries to prevent to act as a deterrent for lorry drivers to overload the lorries. So basically, there are strict standards for trucks, and the one country where you can see severe overloading of trucks is India. But in Sri Lanka, generally we try to avoid it, because our road conditions generally do not allow us to overload too much, because our roads have a lot of bends, sudden steep sections, and so on. So if you overload the lorries, it's very difficult for a lorry to negotiate that type of situations. But if you look at countries like India, you see severe overloading of lorries and trucks. But in Sri Lanka, generally we do not resort to that type of practices. If the heaviest vehicle that you get on the road could be about 40-ton truck. But then again, you would have seen prime movers pulling even 1,200 bags of cement. But what you see is they have more axles. Because they have more axles, again the impact of such vehicles will not be that significant. A shorter vehicle with a heavy load can be much more significant than a longer vehicle with a heavy load, because the longer vehicle can have so many additional axles. So and then sometimes the effect of modern codes, for example, Euro code will allow you to go up to 360 ton. So we have to always see what is a desirable load when you are designing a bridge. So if you look at this particular chart, this is from BS 5400 part 2, 1978. So the loading is somewhere here. And here you can see up to 30 meters, 30 kilonewtons per meter per lane, which gives a value like 8.5 kilonewtons per meter squared with a road width of 3.5 meters. With a road width of 3 meters, you can get a value like 10 kilonewtons per meter squared. Right? So basically what you see is these numbers: 5 for pedestrian load, 10 for vehicle load. That type of numbers are reasonably accurate. And in 2006, so this is the abnormal vehicle. And you can see that overall width of the vehicle is 3.5 meters. Overall length can be, the shortest vehicle can be 3.6 from front axle center to the rear axle center. And there are 4 axles. But it can actually go up to a length of about 30 meters as well, depending on the situation. So you are allowed to increase it in 5-meter increments. And then this is something that happened after the opening of Channel in England. Channel is the Channel tunnel, that allows heavy vehicles being transported by train under the sea, and it's some 30 kilometer long tunnel under the sea, which is now called channel. Channel tunnel is the English channel. The sea is called English channel, and there's a tunnel under the sea. It's called Channel Tunnel, which was constructed in 1990s. And once it was opened, the heavy trucks could easily be transported to England. So they found that the loads that they used as for 1978 guideline may be a little too low, and they should go for higher values. And for about 30 meters, again, you can see this value like close to 30 is okay. But earlier load, it was flat below 30 meters. But in this one, it's going up all the time. But you will find this is one of the heaviest loads that could result in a bridge, on a bridge. So these are all approximate predictions, but this particular prediction actually gives a pretty high value. So basically, then you can look at what the Eurocode says. Eurocode says 9 kilonewtons per meter squared, and you can have this tandem loading where the magnitude is 300 kilonewtons, 30 tons, and here another 30 tons with a small spacing. So you can see all these loads are pretty similar, but you have to consider it differently based on different arrangements. So you can have single axle, single wheel, 20 tons, single axle, 40 tons, or tandem axle, 60 tons. So the distance is 1.2 meters. So you can see now, when you look at all this loading, you can see one important point, and that point is we are going to analyze a lot, because there are so many different loading to be considered. They act all over the bridge, perpendicular to it, and you have to spend significant amount of time with all this loading to work out which gives the maximum, So that is not an easy task. So because of that, these days we always get the help of computer software like SAP 2000 or CSI Bridge or MIDAS, and create a grillage and then apply the loads on the grillage, and then we try to get the maximum bending moments and shear forces. So if you are not familiar with grillages, just read a book or just type the grillage analysis on internet, and you can get enough videos and other information. And if you can get hold of a software like SAP 2000, you can easily create a grillage. In few minutes, you can create a grillage and then apply the loads and see what's going on. So then you can have the abnormal load, and you can see 9 loads of 9 axles, 200 kilonewtons at 1.5 meter spacing. And so this can give a total of 1,800 kilonewtons, so 180 tons. So, and it can actually vary between 600 kilonewtons going up to 3,600 kilonewtons. So if you refer the Eurocode, you can see it allows you to consider different HB type loading depending on the type of highway. Right. Now, before we go into the actual design aspects, I would like you to know what a very experienced bridge engineer taught us in 1990, 11 July 1990, in University of Cambridge. And his name is Robert Benham. And Robert Benham has actually written a book on bridge engineering, which is a very nice book to read, and his knowledge was superb. And he came and said, concrete bridges designed to our codes of practice. When he refers to code of practice, he is referring to the kind of loading and the various partial factors of safety we use in design. He said, practice are not at no risk of failure due to logical actions under the specified traffic law. The search for excessive accuracy in the calculation of transverse distribution of moments due to live loads, for instance, is a waste of time. It's far more profitable to think carefully about the stresses which can arise in a car's in situ bridge deck during construction due to temporary conditions, high initial pre-stress forces, settlements of foundations, and above all, heat of hydration. So you can see, sometimes you find some, even the experienced engineers, they pay a lot of attention to finding the exact bending moment that will act on the bridge, the exact maximum. And then you would find some engineers, they are not really bothered. They look at, they think about the type of loading that can occur. And with their experience, they place the loads at the critical sections so that the bending moments and shear forces will be maximum. And then they get a reasonable answer. And they know for different types of loading, you have so many factors of safety. So if the load, if the bending moments vary by 3% or 4% or 5%, it is not going to make any significant effect on the bridge design. So they just, after some analysis, they get a reasonable looking bending moment diagram, which looks pretty accurate, not exactly. Then they would go ahead with the bridge design. So on the other hand, there are some other engineers, they spend hours in front of the computer just to find the maximum bending moment. So basically, if you look at this statement, you can clearly see, if you start with a reasonably accurate bending moment, shear force, torsional moment, determined by using a reasonably accurate relay analysis, then you are through. You don't have to worry too much about the actual maximum values, so maximum shear force values, so bending moment values, because there will be adequate factor of safety. So what are the steps in the bridge design? When you are designing a bridge, what are the steps? The steps are, first you have to get the preliminary design done. That is the most complicated thing, because although we say preliminary design, you have to get all the parameters right, almost right, and then you can use the detailed design to check it. And we had one Professor T. Mayabel as our external examiner. He was the past president of Institution of Structural Engineers, London, in 2015. So he's a very brainy person, and he says, okay, this is the fun part of design. So you are not dealing with complicated analysis or anything, but you are looking at your deep knowledge, your knowledge base, and you are trying to come up with something reasonable, so that the bridge, the detailed calculations can be performed for what you have found at the initial stage by using various approximate methods. But you try to arrive at a reasonably accurate solution without doing many calculations. So that's a real challenging part of bridge design. And once you get a solution, then you have to check that solution to see whether you have got all your calculations right. And that is a part of the design, that that any routine set of calculations would be ignored. So anything routine these days, you'll find somebody will write a computer program. And so you could see that, you know, most of the detailed calculations can now be performed by the computer, and they can even produce calculations to suit various codes of practice. So that's another thing you can see. So, for example, MIDA Civil or CIS bridge can easily handle and produce many calculations that are very accurate and well presented. But always you have to make sure your preliminary design is so accurate, so that represents a good arrangement for a bridge. So I will skip this reinforced concrete bridge part for the time being, because I want to discuss about the precast beams and how the bridges have evolved before we go deeper into the reinforced concrete bridges, where we have to learn concrete technology, and also we have to learn you know, the principles of optimizing concrete bridges. So those are things we have to discuss. But before I go any further, can I ask what's the time I have to end the lecture? Engineer Kamala? Oh,
8:30, sir.
8:30, right? Okay.
Yeah.
Right. 8:30, yes. So before we look at reinforced concrete bridges, we look at little more about the evolution and construction, because, you know, if you want to design a good bridge, first you have to have a reasonable idea about the construction aspects of it. Then only, you know, we can convert all these construction nodes and associated other nodes to the design. Otherwise, you know, you might do the design only for live nodes, and you might find the construction, the nodes that occur during construction can be as critical as the maximum forces and moments due to the live load scenario. So because of that reason, it's good to know about various construction aspects of it. So if you look at this diagram, and here you can see that the bridges, the beams are placed touching each other, and then it's filled with concrete. And these are standard beams by Costain Domecq. And you'll find in Sri Lanka also we have adopted very similar dimensions, only minor variations by Road Development Authority. So very similar dimensions for bridges, and this type of bridges can be used up to 18 meters. And one of the key things you have to appreciate is if you consider self-weight of the bridge, it can be about the bending moments caused by the self-weight of the bridge might be about 200% the bending moments caused by live load. So you can see the dead load is much more than the live load. When people realized this, they thought, okay, this might be okay for shorter spans, but if you are going to go for longer spans, like 30 meters, then you know, filling the whole deck with concrete is not a very good arrangement, because it's very heavy. Then they went for this arrangement. Now you can see it's the main drawback is you cannot inspect anything from below, because the gap is only 30 millimeters between two beams. So you cannot inspect what's going on, whether the bridge is deteriorating or whatever happens. But significant reduction in the weight of the bridge. It's very significant reduction in the weight of the bridge, and this is called MB. And then later in 1990s, they actually developed what he called Y-beam. The speciality of Y-beam is you don't have to place it touching each other. You can place them at 1 meter interval, but there will be a gap. And you can even place them at 2 meter intervals. So here you can see Y-beams at 1 meter centers or Y-beams at 2 meter centers. So the small spans are Y-beam at 2 meter span, 2 meter spacing. This longer span going up to 31 meters is Y-beams at 1 meter interval. And the Y-beam dimensions, sectional dimensions, everything is given in the chart. And so by using this particular chart, you can work out the arrangement of a Y-beam, and by using this particular chart straight away, you can say what is the type of Y-beam, the dimensions of the Y-beam, and generally we go for a top slab of minimum 160 millimeters. But in my case, I prefer some value like 200 millimeters for the top slab with 2 mats of reinforcement. And that can give a very satisfactory behavior for this type of bridges. And so the arrangement would be something like this. So these are very economical arrangements and widely used whenever you have an obstacle like a river or a road, where in the case of road and river, you don't like the boat movement being affected, then these are ideal solutions because very easily you can place these beams after closing the whatever underneath for 1 or 2 hours. You can very quickly lift and place the beams, and then connect them all with reinforced concrete top deck, giving a composite construction. The advantage of composite construction is once the concrete gains the strength, the depth of the section will increase, but now it's a thicker, deeper section, and all this deeper section is now available for carrying the live loads, because we are carrying live loads on a reasonably lightweight deck. We can reach a significant economy. So the spacing can be 1 meter going up to 2 meters. So if you look at our scenario in Sri Lanka, you are familiar with this type of long span bridges, flyovers like Wadon Kandy A1 road, and then you also can find another one at Dugegoda Junction. So these are flyovers that those go to Sri Lanka. And then I have one of my friends, Mr. Atula Tantri, who manufacture trailers. And once during this time, this was about 15 years ago, we did all these bridges. And one day he met me and said, okay, Prof, I actually went and measured all these bridges and to see whether we can manufacture this type of steel bridges in Sri Lanka, because he's having a lot of sophisticated cutting machines, because his company manufacture most of the 40 the flat decks, flat beds that will carry 40 ton 40-foot containers. So basically his company has a lot of facilities for fabrication and manufacturing of steel sections. So he said with his facility, he can easily manufacture this type of bridge in Sri Lanka, and he can manufacture it in such a way it can be prefabricated and then fixed at the site. So you can see we have some technology, people having sufficient machinery, but we hardly give them the work. And if you look at this particular train carriage full of people, the same company used to repair these are called Romanian carriageways. And these Romanian carriageways, his company used to repair at a cost of 10 to 13 million per carriage, whereas if you are bringing one to Sri Lanka, it will cost 400,000 US dollars, 400,000 US dollars per carriage, whereas he used to restore them only for a fraction of the cost. And the last order he completed, he told me that no, it was 50 carriages completed at the cost between 10 million per normal third class, and second class you can be around 13 million. And he told me that he completed 50 carriages, but because there was a huge price escalation, he could not get any price escalation, he was not offered. So he made a big loss of about 400 million rupees, but still he completed the project. So there are people and technology in Sri Lanka to manufacture bridges in Sri Lanka. So why I told you that is, otherwise we think whenever we have a big steel bridge, we have to import it, as we have done in this particular case from England. And then this is one figure, and this is how it looks like from below, with so many bracing arrangements, and even lot of web stickers for the beam to prevent buckling of the steel sections. And I think this is the Dehiwala flyover. And you might ask, what is this? Singapudi Bridge at Punareen. And how would this come here? This is actually the flyover meant for Panadura. This is a Panadura town flyover, but due to some reason they found that it's not necessary, and then it ended up connecting Jaffna Peninsula with the mainland at Pune, and this is called Sangapudi Bridge. But if you look at this particular bridge, I would say it's a mistake, because now this bridge is directly over the sea, and the chances of corrosion can be high. So it would have been far better if they have actually galvanized this bridge, whatever the sections that were brought to Sri Lanka, if they have hot dip galvanized, then this bridge would have lasted much longer. There was one bridge built by German aid in 1962, and I found that particular bridge is fully galvanized. They have galvanized it. But earlier we used to have bridges where we used to, we didn't have painted it. We painted it with bitumen. And those bridges lasted very, very long times. Because bitumen could give a near perfect protection against corrosion. But today we rely a lot on paint systems. But sometimes these paint systems can give us some trouble. So this is may not be a very good solution, but anyway, they have actually constructed it. And then you might ask, what is this? This is the Orugodavat flyover, and again you can see there are 4 lanes. But the main difference between this particular long span bridge, which was 550-600 million with lot of extra work for pipe diversion, whereas for a single span, sorry, 2-lane bridge, this is a 4-lane bridge, 2-lane bridge having a length of about 300 meters. We read on paper the cost would have been about 800 million. So you can see 2-lane bridge cost 800 million, 4-lane bridge costs less than 600 million. So there's something wrong somewhere. Right. Now you can see the type of cross section of Orugodawath flyover, and you can see they are actually the width of the deck is 17.6 meters, and you can see the value engineering solution we developed is having only 4 box girders. Earlier, the Road Development Authority completed design had about 10 beams. So we reduced it to about 8 beams. And by doing so, we actually made a big saving. And this bridge was something that I actually designed as a value engineering solution. And this is the Mattakpulya bridge. This bridge, although it was fully completed, the access roads had many problems, so it was underutilized for a long period of time. And this bridge is also across Kalari River. And if you ask the cost of this bridge in late 1990s or early 2000s, the cost of this bridge was only about 210 million. 200 million. The original estimate was 210 million, but later it was completed for 200 million. The project manager, project engineer was Mr. Chandasiri, one of the well-known bridge engineers, who was later responsible for getting the Southern Expressway open up to Hall first and then up to Mathura. A very dedicated bridge engineer. And if you can get an opportunity, please invite him to do a lecture. He's retired and he might not be very active in doing engineering work at the moment, but he for about 5 years he worked in the Central Expressway section 1 also. So if you can get him to do a lecture for you, it's a bonus because he has vast knowledge with construction and design of bridges. So basically what he says, he's very capable and he can design a bridge on a half sheet. So on a half sheet, he will do all the calculations and complete the design. So he's a very capable person. And this is the Orugodawath flyover. This is the Mattakpulya flyover. So you can see these box type beams. And then this is another bridge that I actually helped Engineer Vansena of Maga Engineering to complete for Maga Engineering. This is again a value engineering solution. This original design was by Engineer Nivara Chandasiri with raw foundation, but later foundation. So I was asked to help them. So I actually helped them with the design. A value engineering solution that actually is in a big saving in the cost, and this is having five spans, and the same design was used in a three span bridge, and each span is 25 meters of eye girders that were precast and post-stationed at the site. So this bridge was completed in a very short period of like 4 months. And this is another view of the same bridge. And then we also used a special detail to avoid expansion joints in this particular bridge. And if I can draw and show you the type of detail that we used. This is the same detail that we adopted for Orugodawath flyover as well. So what we do is we get the precast beams, and then we cast the top slab continuous. So this can be about 200 millimeters, and this can be about 1.5 meters. And what we do is, after making it continuous, we place some dowels and we cut a groove and fill it with polysulfide and lay the asphalt. Lay the asphalt on that. So when you cut it, you can see actually it's connected by a dowel. Here you get a dowel, and so no movement can occur, and you find the crack forms under the dowel as well. So this way, you know, on the road you cannot see an expansion joint, but if you look at the behavior, because of the presence of these dowels that are free to move, and how you might ask, how do you make a dowel and then allow the beam to move freely? What you do is, before you do the concreting, we'll wrap a polythene sheet around the steel rod, and then we'll continue our casting. So once the casting is over, you'll find that there's a correction, but it's flexible. There's a correction between two adjacent beams on each span, and there's a connection with the dowel, but not complete connection. Any minor movement can be easily accommodated. So this is the kind of joint that we adopted at this particular bridge, as well as Orugodawatta flyover. And so you can see you can use I-beams, and one of the key things that you have to keep in mind is it's safe if we can actually go for 200 millimeter top deck and with two mats of reinforcement. And generally in the transverse direction for bottom reinforcement, we use T16 at 150. But all the other reinforcement can be T12 at 150. And sometimes you might find that, you know, even T8 at 150 can be used in certain spans, not everywhere. But the common detail is T16 or H16 as the bottom mat in the longitudinal direction, and then transverse direction T12 at 150, and in the top mat in the transverse direction T10 at 150, T12 at 150, and in the other distribution direction you can even use T8 at 150. So you can see a deck of a slab will have a lot of reinforcement, and because of these reinforcement, you will find that it can actually give a very robust type of bridge, because when you consider the load of 10 kilonewtons per meter squared acting on a deck of 200 millimeter thickness with two layers of reinforcement with bottom reinforcement at as H16 at 150 millimeters. H means high yield bars, and these high yield bars are manufactured by using QST technology, quenched and self-tempered. And if you look at Langwa, Melwa, all these steel, GTB, all are based on this QT. They call it shortened form QT technology, quenched and tempered. And the actual word is QST, quenched and self-tempered bars, where they actually pour water when the metal is red hot. Immediately after making it to the right size, it is you pour water on it, and that will create a very hard outer crust. But then they will move it, allow it to cool down on its own, because the reinforcement has a soft interior which actually cools down very slowly. You'll find this bar can be easily bent, but it's super strong. The reason is interior is still behaves like mild steel, exterior behaves like high strength steel. And because of that reason, the average strength can go up to about 500 megapascal or 500 newtons per millimeter square. So I think we are close to 8:30, and what we can do is we can continue the same the remaining part of this lecture coming week, and then we'll move to the concrete technology aspect of it, of bridges, and also how to deal with reinforced concrete bridges. With that, shall I stop?
Yeah, Professor, thank you so much.
Thank you.
Great presentation. Engineer Bandukar, I invite you to do the vote of thanks today.
Yeah, dear sir, it was a very informative session and a good introduction for the lecture series. I want to express our sincere gratitude to sir for sparing your precious time from busy schedule to conduct this lecture series. Actually, this is the first session out of 8 sessions, and there were many positive responses from practicing engineers, and there were around 170 participants for this session today. So I would like to thank again, sir, for your conducting this lecture series. Then I would like to thank Civil Engineering Sectional Committee Chairperson, Engineer Kamala Gunawardana, for the leadership to conduct these kind of productive sessions, and all the subcommittee members for arranging this. And further, I would like to thank the IESL Secretariat, Publicity Department, and IT Department for the hosting arrangements. Last but not least, I would like to thank all the participants for this session. And we will inform you about the next session. It will be on next week. So we will inform you back. And thank you again, everyone, and have a great evening.
Yeah, thank you very much.
Thank you. Good night.
Good night.
Thank you. Thank you.